nanohub.org.
Online simulation and more for nanotechnology.
Okay, so welcome back to week 1. This is module 1.2. And as we discussed in the first module, what we want to talk about is how you think about the resistance, or the conductance is actually just the inverse of the resistance. So sometimes we talk in terms of resistance, sometimes we talk in terms of conductance, which you write as G. And what we'd like to talk about is how you think about this conductance or resistance of small devices. And for this, I'll be trying to describe to you a different viewpoint, different way of thinking about this, which needs a couple of concepts that I want to get across in this module. And the first concept is this idea of a density of states. And that is that, you see, we are trying to describe the current flow through this channel. And one of the first things you want to know about this channel is this density of states, which is what I've sort of plotted schematically here. Along the vertical axis is energy. Along the horizontal axis, I have this what's called the density of states, which tells you how many states you have per unit energy at that particular energy. So let's say you're interested in some energy here, then this density of states value here tells you how many states per unit energy. Now, one of the things you know is, like if you looked at an atom, for example, you would have discrete states like this. Like in a hydrogen atom, there is this 1s level, and then there's a 2s, 2p, etc. Now, when you get to bigger things, what happens is you have more and more energy levels. So the bigger you make it, a lot more of these levels here. And when you get to something relatively big, you have lots and lots of states, so that if I were trying to draw all these states, I'd be drawing lines forever. So instead, a convenient concept is to draw this density of states, which tells you that in a given energy range, how many states do I have? So the answer, so this quantity D of E may be, say, 20 per electron volt. And I should mention here, this unit of energy, as you know, the MKS units of energy is given by joules, which is a coulomb times a volt. So that's the MKS unit of energy. And in general, for everything we discuss in this course, we'd be using the MKS units. Except for this energy, it's just more convenient to talk not in terms of joules, but in terms of something called the electron volt. And the electron volt is like an electronic charge times a volt, rather than a coulomb times a volt. And an electronic charge happens to be this 1.6 times 10 to the minus 19th coulombs. And so this electron volt is actually a much smaller unit than joules. It's like 1.6 times 10 to the minus 19th joules. And this is a much more convenient unit when we are talking about the energies of electrons, because otherwise you'd be using this 10 to the minus 19th all over the place. In fact, one of the common mistakes when getting started is you tend to get answers where you get 10 to the minus 19th in the wrong place because you forgot to convert units properly. Okay. Anyway, so getting back, the first concept I want that one needs to get used to is this idea of a density of states. Now, where does that come from? Well, one point I always stress in science and engineering is that most of these concepts usually have a basis in some experiment. There is an experimental way of measuring these concepts. So, for example, the density of states, the way you would measure it experimentally, I guess the most common method could be based on the photoelectric effect. That is, this effect that was discovered about 100 years ago, that in any solid, if you have electrons, if you hit it with light, electrons are emitted out into vacuum, out from the solid. So let's say this is the vacuum level. What that means is, when an electron is inside this solid, these are its energy levels. Once it is out, that's when the energy is somewhere here. And so if I want to knock an electron from inside the solid out here, what I have to do is, I have to hit it with light whose energy is large enough to take the electron from here and place it outside the solid. So that's how photoelectric experiments are done. Photoemission spectroscopy experiments. Hit it with light, you see what h nu, what photon energy is needed to knock an electron out of that solid. And that is how you'd get information about these levels. Now, I'm not going into the details of this. And for example, obviously you could use this method only to investigate the levels that are filled. Because if there's an electron in a certain level, you can knock it out. But in a solid, there's always some states that are filled and some states that are empty. That is, and usually one draws a line, call this electrochemical potential, mu, or Fermi level. Those words we'll be using almost interchangeably, which tells you the level up to which the states are filled. And above that, the states are empty. Now, if you have empty states, then you cannot really measure it with photoemission spectroscopy because there's no electrons there to knock out of the solid. You know, the electrons are all filling up these levels, everything below mu. So you can hit it with light and see it come out of the solid. When you have empty states, you cannot quite do that. But there are other techniques for looking at those things. Things like inverse photoemission spectroscopy or optical absorption, which I'm not going into because the main point here is that there is this concept of density of states which can be experimentally measured. They can be modeled based on different theoretical models, which are based on quantum mechanical models, which actually are more a part of the second course. And in this course, we really won't be talking about the models very much. We'll assume that, well, from various sources, we know what the density of states is for this channel. And then the question is, how do I calculate the current flow? How do I estimate the resistance, etc.? But, right. Now, so that's the first concept I wanted to get across, the idea of a density of states. The second concept is that of this electrochemical potential, the idea that all states are filled up to a certain level and empty above it. Because there's two concepts going in there. One is that when you have a whole bunch of states available, the electrons want to go to the lowest energies that are available. So it tries to go into the lower energies, leaving the upper ones empty. But you might say, well, then why doesn't it just go to the very lowest one? Why does it have to fill it up all the way up to here? Well, that's this exclusion principle. The idea that one level can only contain one electron. So if you have a level down here and you got 10,000 electrons to accommodate, you can't put them all in the same one. You need 10,000 levels to accommodate them. And so they always have to be filled up to a certain level so that you can find 10,000 states to put them in. So this exclusion principle and the idea that everything goes to the lowest energy kind of gives you an idea of, why there is a line like this in energy, the electrochemical potential or this Fermi energy, which separates the filled states from the empty ones. Now, to make this a little more quantitative, and that's the second function that I want to explain, that's this Fermi function, f, which is usually written as f of E. And this is a function that tells you the occupation of these energy levels. That is, d of E, the density of states, tells you the availability of energy levels. But then just because it's available doesn't mean there's an electron there. It could be empty or it could be filled. And this Fermi function tells you what is the probability it's occupied. Now, based on what I just said, you might say, well, Fermi function should look something like this. So this axis is energy, and I'm drawing the Fermi function. So you might say, well, didn't I just say that everything below mu is filled and everything above mu is empty? So in that case, the Fermi function should look like 1 below mu and 0 above mu. So I would expect a function looking something like this. Now, some of you actually may have seen this Fermi function before. Main thing I should mention is that usually it is not, you usually draw it kind of turned around. And so if you are used to seeing that, it might take you a little bit of effort to get used to this way I'm drawing it. Because normally what you do is, you draw the, what you call the independent variable horizontally. So you tend to draw E in this direction, and f of E, the Fermi function, in the vertical direction. And so, the function might look something like this. It is 1 up to some energy, which you call the electrochemical potential or the Fermi level, and 0 after that. So, this is the form in which you may have seen the function. And what I'm drawing here is the same thing, but kind of just turned 90 degrees. And that's because when you're drawing energy, you usually draw it in this direction. And so by turning it around, the Fermi function also has the same axis in the vertical way. Okay. Now, this is exactly what the Fermi function looks like at 0 temperature. That's when everything up to mu is precisely filled, everything above mu is empty. Now, at non-zero temperatures, this thing is somewhat diffuse, this boundary. That is, what happens is the picture looks something like this. So, if you go way below the chemical potential, it becomes 1. And if you go way above it, it becomes 0. But there is an energy range here, over which it changes from 0 to 1. And that energy range is of the order of kT, where K is the Boltzmann constant and T is the absolute temperature. Now, up to here, what I said, that everything's filled up to mu, there is a simple physical argument for it. Namely, well, all electrons go to the lowest energies and there's an exclusion principle. But why it is spread out over a range kT, that requires a much longer discussion of equilibrium statistical mechanics, which we are not going into. So, what I'll simply state is the actual form of this function, this Fermi function, the mathematical form of this function, which I have sketched here, basically. And the way what the Fermi function looks like, let me write it here, is the following. Maybe I'll write it as exponential. So this is the mathematical form of the function. And what you can check is that if you take this and plot it as a function of E, which you could do if very easily if you have something like MATLAB or equivalent, you could easily check, it would look like what I've sketched here. And you could argue that when E is very small, much below mu, what happens is, this is a large negative number. An exponential of a large negative number is almost 0. And so the Fermi function becomes 1 divided by 1 plus 0. On the other hand, when the energy is way above mu, way above this electrochemical potential, then this is a large positive number. And we are talking of exponential of, say, 100. And that's a very big number. And so when you divide 1 by that big number, it becomes 0. So that's how you would understand this picture. And this transition from 1 to 0 takes place over an energy range of the order of a few kT right around the electrochemical potential. So these are the two important concepts that we need in order to discuss current flow. And first being this density of states, d of E, and the second, this Fermi function, f of E. Now, another additional point I want to make is that usually if this whole thing is in equilibrium, then you have a common electrochemical potential all the way. So just as you have an electrochemical potential on the left contact, which tells you, how far it is filled, there is a similar thing for the right contact. And at equilibrium, they are both the same. Now, when you apply a voltage across it, so let's say you have a negative here and a positive here. What the positive voltage does is, it takes what is in this contact and lowers it with respect to what is in this contact. So, what would happen then is, when you looked at the other contact, you'd see a different electrochemical potential mu2. So, I'll have a mu1 in the left contact, a mu2 in the right contact, and if I was to plot the Fermi function in the right contact, it would look something like this. So, to sum up again, concepts are density of states, that's in this channel, and then you have these two contacts which are like two big reservoirs, which are filled up to this mu1 and mu2. At equilibrium, the two are the same. You could almost think of this mu as the level of water in a reservoir. That's the level up to which this one is filled. That's the level up to which that one is filled. And corresponding to this mu, there's a Fermi function that describes how electrons are distributed in that contact, which come into this channel. Same here. And at equilibrium, those would be identical. When you apply a voltage, what happens is, everything in this contact is lowered with respect to that contact by an amount equal to this applied voltage. That is, if I apply 1 volt, then all the energies here are lowered by 1 electron volt. So this difference here is 1 electron volt, which is like Q times V. So V is the applied voltage, Q is the charge on an electron. I think I defined that, stated that earlier. This Q is this 1.6 times 10 to the minus 19th coulomb. And the charge on an electron is the negative of that, actually. As you know, electrons are negatively charged. And the point is that this contact is then, everything here is lowered by an amount QV compared to that contact. And that's when current flows. It is, if the two mu's are the same, then no current will flow. When you have applied a voltage and separated them, that's when current can flow. And that's what we'll talk about in the next module.